Hi. In this second video of forces, we're going to just continue from where we left off. And we were looking at the forces involving in lifts. Now, we start this video with a worked example of a lift problem. And then we're going to move on to looking at free body diagrams and how important free body diagrams are when doing problems involving forces. Especially so, especially so when the forces involved are at an angle to horizontal or vertical, and we need to split those forces up into horizontal and vertical component parts. And so we'll go in and do quite a bit of detail on that. There'll be lots of worked examples, but can I stress how important a free body diagram is? If you're doing that, you really must, wherever possible, draw a free body diagram. It will really help you. Okay, so yesterday we looked at lifts, tension. I said for you to have a look at this problem, take a photograph of it, and complete the problem. Now what we had is we had a lift, and the lift was accelerating downwards at 3.4 meters per second squared. There's a Newton balance suspended in the lift, and that Newton balance has a mass of 2 kilograms attached to it. And what you had to do is calculate the reading on the Newton balance. So the fact that the Newton balance is in the lift is really just to confuse you. It has very little bearing on what actually needs to be done in this question. You can almost entirely ignore the lift and just focus on what's happening to the mass itself. So, free body diagram. The mass is attached to the Newton balance by means of tension, and the Newton balance is just going to read the tension. The mass will also have a weight. Now, it's accelerating downwards. We have it 3.4 meters per second squared. And so our unbalanced force must be acting downwards. This means the residual force from the weight minus the tension. So our tension is going to be less than weight. We work out what weight is, and we work out what unbalanced force is. So fun is MA, 2 kilograms, 2 times 3.4, 6.8 newtons. Our weight. Two times 9.8, 19.6 newtons. And so the tension in this case will be weight minus fun. And that's going to give us 19.6 minus 6.8. And that's going to be 12.8. T is tension. Oh. So the reading on the Newton balance will be 12.8. Okay. Now, free body diagrams. I was saying yesterday, free body diagrams, super important. Draw a simple shape, like a circle or a box. The arrows of the forces must be attached. So tension and weight must actually be touching the surface. We don't need to include fun in our free body diagram because fun isn't actually a force being applied to the object. The fun is just the residual or the resultant force of whatever forces that are acting on it. So that's why we can just include fun over there. That's just to say that the fun is a direction. Okay, moving on. Sorry? Another time. Resolving force vectors. We've obviously had forces, and up until this point we've been looking at forces that are purely linear, so i.e. only in the vertical plane or only in the horizontal plane. But quite often we will have forces that are not in either horizontal or vertical planes. We'll have forces that are an angle, and the thing to do, similarly to our velocities, we will resolve these into components of horizontal force and vertical force. So resolving force vectors. If we have force that acts in this direction, so let's call that F, and it acts at an angle theta to the horizontal, we will get horizontal and vertical components of this force, and we'll just use SOHCAHTOA. As with any vector addition, we can take this vertical component and we can transpose it over to here. And so we'll call this force vertical. And we have force horizontal. Now we have SOHCAHTOA. So in this case, for force vertical, we have opposite theta, which is sine. So vertical sine theta is equal to FB over hypotenuse, which is F. If I rearrange this for FB, FB is equal to F sine theta, and horizontal was adjacent, so we'll use cos theta FH over F FH F cos theta. Okay. It's useful to remember these formulas, but be warned. When we come to doing projectile motion, we'll have similar formulas for working out the components, the horizontal and vertical components of velocities. And you'll get very used to just using these formulas. So vertical velocity is v sine theta. Horizontal velocity is v cos theta. Now I've told you here that vertical force is F sine theta and horizontal force is F cos theta. While it's useful to remember these, especially with forces, it is not always the case. Use your free body diagram. It becomes even more important now your free body diagram to actually know which is the horizontal force and which is the vertical force. Okay. With projectile motion, what was I saying? With projectile motion, theta is always going to be along the horizontal. You're always going to have something that's launched at an angle from the horizontal, and so it will always be v cos theta and v sin theta. It will always be like that. But with forces, you could have any number of things. I mean, you could have a pendulum that's suspended from the ceiling, and your theta is now being taken in relation to the vertical rather than in the horizontal. So be warned. Just make sure that you know your trigonometry and your free body diagram is doing the right thing. So it's so crucial to draw free body diagrams for all of these. Okay. So let me give you an example, or a couple of examples. So example one. And we're just going to have so we can have a mass, 3 kilogram mass, and we're going to pull it at an angle of, what shall we say, 30 degrees to the horizontal. And we're going to assume friction free, and then we're going to work out motion. We're going to see what it does. First of all, we're going to split up the forces into component parts. So I'm going to start free body diagram. I'm going to have 30 degrees vertical force and horizontal force. 30 degrees, so I can just use these up here. So F H is equal to, oh, I need to give you a magnitude of the force, don't I? Let's say 10 newtons. F cos theta 10 cos 30. .66. And we'll get F B. Newtons. Okay, so from this, you're going to work out the motion. Well, question number one, I guess, is pulling this block with a 10 Newton force, is it going to lift up off the ground? Why not? Get a free body diagram just showing vertical forces. I've said that the vertical force acting on it is 5 newtons. What's the other vertical force acting on it? mg, which is going to be 29.4. 29.4 newtons. Yeah. The upwards force, the vertical force that we are applying to it, is not going to overcome weight.
And so you'll have, to complete this, it's resting on a surface, obviously. You're going to have 5 newtons of force going to be applied from the string or whatever, and the remaining 24.4 newtons will be a reaction force from the surface. Okay, so that is why it will vertically not move. However, if it's friction free on the surface, we have an unbalanced force horizontally of 8.66 newtons. So it's friction free, and therefore this is going to be fun. MA. We can work out acceleration equals F over M. Over its mass. Call it 2.9. So it will accelerate 2.9 meters per second to the right. Okay. Example 2. Pendulum. Degrees. Okay, so 2 kilogram mass. In order to hold it at an angle of 15 degrees away from the vertical, I need to apply a force going this way. We need to calculate this force. So what is the force acting in this direction? Okay, so let's work out what the forces that are acting on this are going to be. Again, let's go to Freebody diagram. Well, we're going to have a force going this way. You're going to have a force coming down this way. So this is going to be weight. This is going to be, I'm just going to call it F, or I could say it's applied force, FA. And then also we're going to have tension. Now tension is going to be doing that. Okay, so we have 3 forces, because in order to make the pendulum move out here, we've got to overcome the weight, but in doing so, because it's attached to the ceiling, we're going to impart a tension onto the string as well. So our free-body diagram is going to look something like this. What we can say is that the resultant of our applied force and weight is going to equal tension. If we take FA, add that nose to tail, then we'll have a resultant. That resultant must equal tension. So tension and the resultant are going to equal each other. And so that and that, they're the applied forces. You're getting a resultant tension in the string because you're holding it out like this. So we can calculate, well, we can calculate tension. We can calculate the force required to pull a 2 kilogram mass to an angle of 15 degrees. We have a known, and that known is mg. So 2 kilogram mass times 9.8 gives us 19.6 newtons. We also know this angle is 15 degrees because that's 15 degrees with the vertical, then this is the vertical, which is gravity, so this is the weight, and so it will make a similar 15 degree angle in here. So if I know this, no weight, I need to find FA. I can use trigonometry. I'm going to use tan. Opposite over adjacent. In this case, my opposite is FA. My adjacent is W. Rearrange for FA. So that's going to be W tan theta, which is going to be 19.6 times tan 15. We can work out the tension as well. Let's stick with our weight. So calculate tension. Tension here is the hypotenuse. If our weight is adjacent to the angle, we're going to use cos theta adjacent over hypotenuse. So the tension there is the hypotenuse, we've got weight, we've got tension. To calculate tension, we're going to have weight divided by cos theta. And that's going to be 19.6 over cos 15. We get 20.3. Okay, a couple of examples, just really simple forces applied to objects, but as you can see, it can start to get quite complicated. You've got to get your free body diagrams right. Can't quite remember. I'm not sure if you're ready for Helga yet. I can't quite. There's Helga, but I don't really know. She's a shop fitter from Dingwall. Yeah, let's see. Yeah, okay. Let's go. Let's do Helga. Right. So Helga's shot is 7.2 kilograms. Because of her huge stature of 151 centimeters. Is that about 5 foot flat? She's wider than she is taller. She is aspiring to compete at the Commonwealth Games, but right now she can only pull the shot with a complete force of 50 newtons, and she makes an angle of 50 degrees with that. Calculate the acceleration of the hammer, assuming that there's no friction on the surface. Okay. So, again, start with the free body diagram. The applied force is here. We'll have a vertical force and we'll have a horizontal force. Add vector nose to tail. Now, we all know that with an applied force of 50 newtons, she ain't ever going to be lifting that shot up off the ground. It's going to have a weight of 72 newtons. Yeah, no chance that 50 newtons, forget about it. So I'm not too worried about my vertical force, but I want to know what the horizontal force is. And so I'm just going to focus on FH. I know that that's 50 degrees. FH is cos. F cos theta. Cos 50. Which gives me a force of 9.6 newtons. To find the acceleration of the hammer, we then can use A, F over M, 9.6 over 7.2 kilograms. We have 1.3 meters per second squared. So the acceleration of Helga's hammer is 1.2 meters per second squared. I doubt very much she is going to try harder, Helga. Okay. Here's one for you to do. Now, right, so we have who do we have? Bob. Bob has a mass of 67 kilograms. Patty and June are standing either side of a big pit holding a big elastic rubber sheet. Doesn't matter if this is real. It's not. But Bob jumps off the cliff and lands. He tries to straddle either side of the rubber band, because really it's not going to be a 3D thing, but either side of the rubber band, which he manages to do perfectly. And eventually he settles right in the middle. There he is. Ow! Either side. And he makes an angle of 30 degrees to the horizontal on both sides. So Bob jumps off the thing, boing, boing, boing. Ow! Paddy and June, hee fine. So fine tension in the ropes. Wait a minute, you didn't tell me there were ropes. Yeah, they are ropes. So find the tension in the ropes. Okay. 67. So Bob weighs 67 kilos. Now, a Freebody diagram. There's Bob, the red spot. It maybe is. Maybe he was just split in half completely, and all that was left is his head, which is now rolling around in the bottom of the pit. Bob has weight. That weight has to be supported, if he's stationary, that weight has to be supported by the tension in two ropes. So, what else do we know? Can we see anything else? Yep. The combined tension must be equal to the weight. So, what's the tension in one of the ropes? So, tension will equal weight over 2. But really, what you're looking for, it's not that simple, because you're only going to have the vertical component of tension, which will equal the weight. Because Paddy and June are going, they're having to pull back. Hopefully that they don't get dragged into the pit full of alligators and sharks with lasers out there. So the vertical component of tension is going to equal half the weight. Do we know an angle? 30 degrees. Okay, go, try, solve, do. Okay.